All right, ready? Let's go home. You guys can learn all this on your own, right? All right. So we're in the nervous system, and right now we're going to cover the peripheral nervous system from the sensory side. There's also peripheral nervous system from the motor side, right? But I'm going to argue that we already covered the motor side when we covered the spinal cord, because we talked about motor efferents going out. So what today and the hell's today? What is it? Friday is going to cover is basically all of our general senses and then our special senses. So everything coming in to our central nervous system, our ability to be able to perceive things in our environment. So these are just a couple of general slides talking about the peripheral nervous system. Sensory neurons also can be called afferent neurons if we're talking about them functionally. Afferent means what? Going toward, right? Going toward the central nervous system. And generally speaking, there's all different kinds of neurons, but sensory neurons are going to be a little bit weird. When we talk about bipolar neurons or unipolar neurons, those are generally going to be sensory neurons. And we're going to see when we get to vision that vision has a lot of bipolar neurons that actually do a lot of the functions of vision. So motor then is efferent. This is the only slide you're going to see on motor. Remember, motor, efferent, that's the response of our nervous system to some kind of sensory input, because we talked about thinking of the nervous system as a negative feedback pathway. All right, so we divide this into general senses, and how do we say, if you were to use another word for general senses, what would you use? Touch. All right, so our general senses are generally going to be our touch sensations. All right, and when we say touch, like, it's easy to say, think about it in terms of skin, and a lot of the examples we're going to use are skin. But think also that we have internal organs, and when we eat too much and our belly gets full, do we feel that? Yes, those are also general senses. When we have to pee, do we feel that? That's a general sense too. All right. So all of these receptors that we're going to talk about are going to allow us to have those sensations, even though a lot of the examples we're going to use are on the skin, because that's what we think of on a day-to-day basis. So general types of somatic sensations, we have our mechanoreceptive, and anything you think of mechano, it's touch. Right? Mechano is touch. So these receptors detect some kind of touch, whether it be physical touch, whether it be vibrations, whether it be tickles, itching. Does anybody else have this soapbox? When you have an itch on your skin, do you itch it or do you scratch it? I hate it. Oh, God. When people say, I'm itching myself. No, you're scratching yourself. That's a motor response. Itching is a sensory response. Anyway, or a sensory bucket. So when we talk about mechanos, I don't just want you to think about touch. I want you to think about all these things: vibration, tickle, itch, as well as proprioception. Words matter. Next semester, when you do your physical exam lab, part of your neuro exam is to assess proprioception. So what does proprioception mean? Our awareness of our environment, our position. Okay? And there are certain spots in our brain that process that information. Thermoreceptive, that makes sense. It takes care of temperature. I don't just want you to think of temperature, though. It's temperature changes. So to detect changes in temperature towards heat or towards cold. And then nociceptive. That's another word that's going to come up, and you should know what it means. Nociception usually refers to pain. Right? So nociception would be pain detection. All right, this slide is actually just saying all the same things we just said, except it's giving you kind of a flavor for the different types of receptors. No, you don't have to know every single one of those receptors, but some of these receptors are going to be on the next few slides with more, bless you, with more information, and you do have to know that, okay? The reason why we call them general sensory receptors and not touch receptors is, one, because it's more than just touch, right? It's vibrations. Two, they are widely distributed through our body instead of specialized in our nose or in our eye or in our ear, all right? So that's why we call them general sensations or general sensory receptors. All right? Again, when we talk about special sensory receptors, which is the topic for the latter half of this PowerPoint. By the way, this PowerPoint lasts for today and Friday. Okay, so we're not going to get through everything today, so don't expect that. And then next week, hormones. Hormones are fun. You're like, I'm done. It's over. Like, I can't pay attention after that. Why go there? All right. Special sensory receptors. Those are very specific receptors that are in very specific locations. So electromagnetic receptors detect light. Where do you detect light? Eyes. Chemoreceptors. Taste. Where do we detect that? Mouth. Smell. Nose. CO2 and O2. You better fucking know this. No? Who said what? What did you say? Okay, aortic arch, carotid arteries, peripheral chemoreceptors. Do we also have a central chemoreceptor? Yes. Okay. Baroreceptors detect blood pressure. Again, where are those located? Kelsey? Same place, right? Aortic arch, carotid arteries. I'm not putting you on the spot. You already said the answer. And then, of course, sound or vestibular receptors, that's all in our ear. Not this ear, inside our skull. All right, so we'll talk about each one of those after we get through with general senses. So every one of our senses, whether it be sight, smell, general, those are called modalities, our sensory modalities. So it's not something I'm going to like ask you questions about, but if somebody says, well, what's that sensory modality? Well, it's smell or it's taste. All right? Sensations are perceived in my finger, for example, not in my finger. Okay? Because my finger has the receptors for touch. Where does that get sent? Spinal cord. Then where? Up to the brain. Ooh, if it's coming from my finger, what part of the brain? Say. Oh, I thought sorry sounded like sensory. Primary sensory cortex, right? So if you said that. You did not, but it sounded like it. Fake that shit. Right? You ever heard of fake it till you make it? All right. Is story of your life? Story of my life, too. I don't know shit about physiology. I do. I remember my disclaimer when we first met each other. Like, I love anatomy. In fact, I love anatomy so much. After teaching you guys, I'm thinking about joining an anatomy society, and like getting more involved with it. Despite the fact that I want to go into psychiatry. Call me crazy. So we have CNS that's connected to that receptor. So it's not just sending that signal, it's how do we interpret that signal? Because if a baby who has not had much 1 day old baby gets pricked on the finger, they're not going to experience that the same way you experience that, right? So it's how it's perceived. And the perception is based on what? Think baby versus you. E word. What did you say? Lifespan. Experience. It's based on experience. So that's how perception or sensations are perceived. From the receptor to the central nervous system to be interpreted. All right? Turns out that every one of these receptors go to a very specific part of the brain. We call that the labeled line principle. One sensory modality, one specific part of the brain. All right? Has a limited range of stimuli. By limited range of stimuli means my finger can detect touch, but it's not going to be able to detect light or sound. That's not 100% true. Can my finger detect sound? How? Vibrations. Good. In fact, that's how deaf people are able to listen to music. I don't know that that's true, but logically that makes sense. You're just like, oh yeah, that makes sense. Who knows what he's talking about? So, let me give this other disclaimer. A lot of stuff in physiology that I talk about and make examples of are not necessarily because I've had experience with it. I know a certain set of facts, and logically this is how it would manifest itself in the world, right? So I want you guys to get there too, because you're going to have to do that with your patients. All right, so let's start talking about receptors and how they work. So if it's a mechanoreceptor, then literally what we're doing is deforming the cell membrane, and that opens channels. So I brought this. Let's assume that's a mechanoreceptor, right? If I press on it, I've opened a channel, right? And then it closes. Okay, that's how mechanoreceptors work. It's not quite that simple because you're stretching a membrane and opening up sodium channels, but that's the basic concept. Chemicals, CO2, H+, they bind, they open up channels. That allows sodium in. Changes in temperature. Again, there's that word change in temperature. That alters the membrane permeability of ions through channels. All right? And electromagnetic radiation, again, alters permeability of ions through channels. There are certain ways that channels are opened through these different mechanisms, and we'll get into those. But what they all have in common, this recording is going to be absolutely terrible. Let's see if this works. What? Struggle is like real. No matter what the receptor is, it's going to result in a change in membrane potential, which will result in an action potential, and that's what's going to get sent to the central nervous system. All right, so depolarization or hyperpolarization. Some things work by depolarization, and most of what we learned works by depolarization, but hyperpolarization is a mechanism as well. All right, so we'll use a general mechanoreceptor right here. Let's say that this line is the membrane of a Pacinian corpuscle. All right, Pacinian corpuscles detect deep pressure and vibrations. So if I press on my skin, that's going to deform that membrane and open up some sodium channels. Sodium goes in. All right. Most of the time, our receptor potential is minus 70. Our resting potential is minus 70. So in this area right here, if I deform, it might go to, what would be another number if it's depolarizing? That would be hyperpolarizing. Minus 60, minus 50. All right, that's in a depolarization direction. Let's say that threshold potential, you guys remember what that means? Pardon? What's needed to cause an action potential. So let's say our threshold potential is minus 55. Okay, so minus 55. All right? And we depress the membrane a little bit. That gets us down to 60. We depress the membrane a little more. We open up more sodium channels. That gets us to minus 55. All right? How does that translate into an action potential? Well, right here, where our roads of Ranvier begin, we have voltage-gated channels. And what opens voltage-gated channels? Changes in voltage. So we just went from minus 70 to minus 55. Minus 55 is the on signal for voltage-gated channels. And so these are going to open up, allow a lot of sodium to go in, and then action potential gets sent down. All right? But you're never going to send that if you don't depolarize the receptor enough. All right? So receptors are all geared towards enough depolarization. If vibrations are not enough to activate the threshold potential in a Pacinian corpuscle, you're not going to detect that vibration. So let me ask you something. We as humans can detect vibration, but we've heard that like dogs or other animals can detect, for example, if like an earthquake is coming or something like that. So what would you say about their vibration receptors compared to ours? What would allow them, and this is me making shit up on the spot, like I didn't prepare for this. What would allow them to detect vibrations that we can't? And be able to predict that earthquake and go ape shit because it's coming and we don't even know it. Pardon? Probably a lower threshold, or actually higher threshold. Well, lower threshold, higher negative number, right? Instead of minus 55, it'd be minus 60 or minus 65. All right? Maybe their threshold is lower. All right, good. So, differences between people might have differences in threshold, all right? And what would account for that are the different types of sodium channels that are being deformed. All right. So all of this slide is showing you that if we're at our resting potential and we depolarize a little bit, we're not going to get an action potential. But once we pass that threshold, then we start getting action potentials. And as long as we maintain past that threshold, we're going to continuously send action potentials.
I'm sorry, I might have missed it. Why was it action potential except for axon?
Why no action potential? You tell me. What's in the axon? What's in the axon that's not here? Pardon?
Oh, that's the voltage.
Voltage-gated channels.
Oh, I missed
right.
it. I was looking down on paying attention.
So the axon is where the voltage-gated channels are. So if you're pressing here, nothing's going to happen because you didn't get the depolarization to activate the action potential. Good. Thank you. Usually people ignore my questions on the PowerPoints. And then I get questions like a couple days later, hey, you have on slide 33. Okay. So usually what happens is if we increase the stimulus intensity, so I lay my finger on my arm, and it's sending action potentials, let's say 1 every second. And I press harder, maybe it's sending 1 every 500 milliseconds. Not 30, 500 milliseconds, so half the time, so twice as many per unit time. Okay, so that increases. Increased stimulus intensity increases action potential frequency. Because what do you see here? They're all the same strength. So we're not increasing the strength of our action potentials, we're increasing the number. It hurts when I get punched in the face because I just got a bunch of action potentials being sent really quickly about that information. Okay. All right. Receptors can respond to a wide array of stimuli, like touch soft, touch a little bit harder. All right, and the reason for this is well, let's look at this graph. If we have, let's say, my finger just laying on my arm, all right, I'm detecting that it's laying there, but if I apply even just a little bit of pressure, I can feel that difference in pressure, all right? So a 10% increase in stimulus strength, so I went from 10 to 20%, for example, resulted in a 35% larger detection, like 35% larger stimulus change. I detected that. But if I'm already applying like 70% of my maximum pressure, I need to press down a whole lot harder just to get a little bit more feel, just to be able to feel a little bit more. All right, so that's what allows us to have a wide array of detection, like in our receptors. Okay, we have a wide range of response from very little to a whole lot. And one of the things that I want to try to impress on you is it's not just feeling something, it's feeling changes in something. When I poke my arm, that's a change in what my arm's feeling compared to normal. If I poke my arm harder, that's a change from just a light touch, right? That's what this is all based on. So that takes us to this concept of adaptation. Adaptation is our ability to not feel or not perceive a stimulus anymore. Right, our ability to not perceive a stimulus anymore. Some receptors are fast adapting. Some receptors are slow adapting. All right. Fast adapting, one of our more fast ones, are Pacinian Corpuscles. Notice that adapts very quickly. Like we apply pressure or we have vibrations, there's a certain point in time where we don't feel those vibrations anymore. We get used to it, right? This is the getting used to it. All right, and that usually happens pretty quickly. But other things, and they have joint capsule receptors and muscle spindles on there as examples, but I'm going to give you the example of the aortic arch. That is also slow adapting. All right, so what that means is that it takes a long time for the aortic arch to get used to a certain pressure. That is good, because if it got used to a certain pressure and that pressure changed, it wouldn't respond as quickly, right? So it's got to be slowly adapting, so it can detect minor fluctuations in pressure. All right, so here are our touch receptors, our tactile receptors. the receptors that we use to interact with the environment with our skin. All right, you've probably heard of all of these, Meissner's corpuscles, Merkel discs. So these are the ones that I'm holding you responsible for. Remember that picture with like, what was it, 9 or 12 different ones? These are the ones I'm holding you responsible for. So Meissner corpuscles, just to kind of show you where they are, right here, this is our dermis, this is our epidermis. So they're very close to the surface of the skin, all right? In non-hairy skin, so my arm right here. Fingertips, lips, eyelids, those are just some other examples of where these types of receptors would be located. Their function, motion detection, and grip control. Of course, eyelids would not be grip control. That'd be really weird if they could. But motion detection, grip control. Their stimulus is skin motion. So if I move my eyelid, right, I can detect that it's moving. Meissner's corpuscles are responsible for that. Okay? Low frequency vibration. Low frequency. What would high frequency be? All right, they rapidly adapt. All right, so you get used to that. If it's moving and it has moved, they're going to stop responding because they're like, all right, you moved. I don't need to detect that anymore. All right, Merkel discs. Somebody's going to ask, do I have to know the receptive field? No. But the receptive field of Meissner corpuscles is different than that of Merkel discs, which has a wider or narrower receptive field. Okay, so I don't expect you to know the numbers, but which ones, basically what that's saying is which ones are in higher density or lower density. All right, so Merkel discs, tip of epidermal ridges, also at the surface. Here would be Merkel discs right here. All right. Their function, form and texture perception. So if I run my hands across this table, I detect that it's relatively smooth. If I rub my hands against Allison's sweatshirt here, she's got ridges in there. I can detect that due to Merkel discs. All right, so differences in texture. I didn't mean to rub you. All right, so their stimuli are edges. Edges. They detect edges. Where one edge ends and the other edge begins, Merkel discs allow you to be able to detect that. All right, corners, curvature, things like that. They are slowly adapting because when you're rubbing your hands across a texture, that's constantly changing, and you need to be able to feel each one of those changes to be able to detect that as a texture. Yeah, these pictures on the bottom where the hand is kind of to illustrate, like Nick just said, generally where they're located. Okay. I spend a lot of time trying to find good pictures. Sometimes they're not good enough, and sometimes I draw them to make them good enough. These were the pictures I could find, and I didn't have time to draw. So this is what we have. All right, two more types. Pacinian corpuscles, which is the example that I've been using. Notice what I tried to do in each one of these. If you see these green things, I tried to highlight where those are. Up here would be another example. Here's a Pacinian corpuscle. You can recognize them really easily because they look like onions, I think. Like onions have different layers. All right? Notice that they are deeper. So if I go up to Nick and I touch him like this, am I activating Pacinian corpuscles? Probably not, right? Because they are deeper. They require more pressure. So their function, perception of distant events in terms of space, not time, through transmitted vibrations. So when my wife asked me to hang a picture on it, which I hate doing because leveling pictures is a pain in the ass, and I'm usually angry after I get done with this project. And I take this drill and I'm drilling in, I feel those vibrations. That's Pacinian corpuscles. Okay? They have very rapid adaptation so that you stop feeling, that feels normal really quickly. Okay? And receptive field, entire finger or hand. So that's much bigger than what you would see with the previous two receptors that are responsible for touch and texture. That's not a texture, that's a brrr. If you can spell that, I'll give you an A. All right, Raffini corpuscles. All right, again, in the dermis, let me see, they are right here. So very near where Pacinian corpuscles are located. So it's deep. Tangential force across. Okay, motion detection, things like that. Hand shape, motion detection. Their stimulus is skin stretch, because if I have a tangential force going across my skin, what's going to happen? It stretches. Okay, or if somebody pinches me, that stretches my skin. All right, slowly adapting, pretty wide receptive field. And finally, everybody's favorite. All right, we're not going to talk about pain theories and gate theory and modulation of pain or anything like that. I just want you to be familiar with pain receptors and how they act. So we have two types of pain receptors. Both are free nerve endings, so they're both the same type of receptor, but one is connected to myelinated fibers and the other is connected to unmyelinated fibers. What's the difference between them? If I'm connected to a myelinated fiber, how does that make me different than if I'm connected to an unmyelinated fiber? Which one? Myelinated. The myelinated sends pain signals much faster. All right? So we generally find that these are located surface of the body and elsewhere. Elsewhere meaning everywhere else in our body, essentially. Any place we feel pain, we will have a free nerve ending that's myelinated. All right? These are slowly adapting. So if that pain happens to change a little bit, we're able to feel that very rapidly. The unmyelinated goes a little bit slower. Again, surface of body and other places. These will detect pain, but they'll both detect pain and temperature. Okay, so free nerve endings, pain and temperature. But these unmyelinated, itching, crude touch. And by crude touch means I feel I got touched, but I can't exactly localize where. Okay? So pain and crude touch. Itch and crude touch. I'm trying to pull this from memory because I didn't prepare for this. If I remember correctly, free nerve endings that are myelinated, the way you feel that pain is like the sharp stabbing or the, what are some other pain-related words? Stabbing, crushing, things like that. The slow would be that dull, achy feeling. So unmyelinated, the dull, achy feeling. So you get stung by a bee, myelinated fibers. That spreads to a dull throb and itching later. Those are your slow unmyelinated fibers. I'm going to have marks all over my skin by the end of this. All right, so I know I've bored you enough with receptors. Let's get into the fun stuff. You're like, this isn't fun. Where does it go from there? All right, so we have these receptors. We have these receptors, and they have to get to the central nervous system. So there are two major pathways, and we're only doing the basics here. The dorsal column medium lemniscal system, dorsal column, and we're talking about the dorsal column of the spinal cord, so they'd be sent up here. This would be the dorsal portion of the spinal cord. Medial lemniscal, so once it gets up to the medulla, I keep wanting to say hypothalamus, medulla, it's going to go up into this, lemniscal means sheet-like. So it's a sheet-like column through the medial portion of the medulla. Thank you. Seriously, I keep wanting to say hypothalamus. I don't know why. Through the medulla. All right. The other is your anterolateral system. Words matter. Antero means what? Front. Lateral means side. So our front side, right around in this area. Anterolateral system. All right. If you look at this slide, just this picture, outside of the fact that one's red and one's black, what do you notice about the difference in those pathways? Okay, anterolateral has a synapse. What else do you notice? One crosses over at the level that it's being detected. The other one doesn't. Okay, one crosses over at the level, and that's where I'm getting. So both actually do have synapses, but at different places. But one crosses over at the level that it's being perceived, that it's coming into the spinal cord. The other crosses over, where do you think? Go back to the motor pathway. What was our motor pathway that we talked about? Pyramids. You guys remember? Pardon? Synapses at the medulla. So same place that motor pathway, and I'm lacking the word too, so I can't bust you guys' chops for not remembering. It would cross over at the level of the medulla. Okay, so that's a big difference between these two, and that's an important distinction to make. I'm going to come back to you for some of your neural stuff. I think it's next semester. And we'll talk about if we have specific spinal cord lesions, how does that affect the way you perceive pain? How does that affect your motor response? Because of this difference in where they cross over. Okay? So, here's how this works. The DCML, because I don't feel like saying it anymore, the DCML, that transmits like our touch, vibrations, Pacinian Corpuscles, Meissner's Corpuscles, right? Position, fine pressure. All right, so remember the receptors involved with that. I just gave you a couple. And I think if you look down in your notes of the PowerPoint slide, it's in the notes too. They contain large myelinated nerve fibers. What does that mean? Information travels fast. All right? there are 3 neurons in this pathway. All right, so you perceived correctly that there was a synapse. There are 3 neurons. The first neuron, sensory receptor, here to the spinal cord and up the dorsal column. Where's the dorsal column? Back of the spinal cord. Okay, so that's the first one. It's going to synapse with a medullary neuron and then cross over and then head up the medial lemniscal pathway. All right, up until it gets to the level of the thalamus. What does the thalamus do? Pardon? No, that's the hypothalamus. Relay center. So it goes up to the thalamus, and the thalamus says, "Hey, I'm being touched on my finger. Let's send that to the appropriate part of the primary sensory cortex." Okay. So that third one's going to send it up from the thalamus to the proper area of the sensory cortex. All right. So 3 nerves in that pathway. All right, same information. None of this is new. There is, throughout the tract, it says here there's a high degree of spatial orientation. What that means is that all information coming from fingers, hand, arm are going to travel up one specific column. Okay? And those columns, here's your columns. This would be one side. This would be the other. Those columns are organized so that the lower limb is more medial and the upper limb is more lateral. So the higher up you go in your body, the more lateral the columns are. And the way this works is, let's say, this is where you guys are going to really make fun of me. I guess that's not as bad as it could be worse, right? All right. These are coming up. Then, as you get up a little farther, these add to the outside, add to the outside, add to the outside, add to the outside. So it builds from medial out, right? These columns. That's what gives us our spatial orientation. Your left arm's a little bit big. Okay. Yeah. What do you mean?
What you just drew, those lines, is that actually shorter, like in the arms, there's less distance to go?
Yeah. Yeah. So yeah, they would be shorter in terms of fiber from the arm to the going up. Right. Yep. All right. So that's kind of how they're organized. Because they're these large myelinated nerve fibers, information's transmitted very rapidly, right? We already said it's fast, and with a high degree of precision because of that columnar organization. We know that I felt something in my foot versus my hand because it's organized that way. All right? That's a good demonstration of that label line principle, right? Sensory modality here is different from my sensory modality there, and it's going to go to this very specific spot up here. All right. Contrast that with the anterolateral system. All right, the anterolateral system's different. All right. First of all, it's going to respond to a much wider array of modalities. So here's specifically when we talk about spinal cord injuries next semester, pain, temperature, crude touch are usually what you refer to these as. Pain, temperature, crude touch. Also tickle, itch, sexual sensations, things like that. Broad spectrum. They travel down smaller myelinated and unmyelinated fibers. So these are going to travel much slower than information traveling up the DCML. LM? DCLM? DCML. Okay. So here there's also 3 neurons, but note how this is different from what we previously talked about. So here's your, okay. If you were to criticize this book, where these pictures came from, touch, vibration, position, yet they show a feather on the finger, but the anterolateral system, tickle and itch.
Dumb.
It's kind of dumb. Okay, I don't like that picture. But here they show a candle. Of course, you're going to get, or they should put Nick's picture there, right? Because we know he's hot, and if we touch him, we're going to get.
I thought you meant I caused pain.
You are. You're hot. You're like. All right.
That's funny.
You're so ugly. Your picture caused pain.
No. Okay. There are also 3 neurons in this pathway. So the first neuron goes from the receptor into the spinal cord. How's that different than the other one? The first synapse is as soon as it enters the spinal cord. How's that different than the DCML?
Crossover in the.
Before that,
It looks like going to a different level.
it went in and up, then synapsed. Here, it goes in and synapses right away. Okay? The second neuron crosses over to the other side and then travels up to the thalamus. All right? What got bypassed here in terms of synapses compared to the previous one? The medulla, right? We didn't synapse with the medulla in this case. It traveled right up through the medulla and went to the thalamus, whereas the other one made a synapse in the medulla, then crossed over and went up. Okay, big difference between those 2 pathways. All right? Then it goes here, and then goes to the appropriate part of our primary somatosensory cortex. All right, here we have a low degree of spatial orientation. So I got burned but it's not very well localized. It's in my, I can tell it's in my fingers, but the specific spot in my finger, unless I see the blister, right, it's very low spatial orientation. Okay? And the reason for that is you don't have the laminar organization, so the upper and lower limb will travel together in the same cord, the same path. Okay? So, know the difference between those 2 pathways. It's really important that you understand and the difference between how those 2 pathways operate. All right, so that takes us to a discussion of dermatomes. And you guys had the concept of dermatomes in anatomy, like the first couple of weeks of anatomy. But here they're coming up again, all right? Dermatomes, by definition, are areas of your skin that are supplied by specific sensory neurons from a specific section of the spinal cord. All right. So the way we kind of look at this, if we look at the spinal nerves coming from cervical vertebrae 2, they will supply basically the back of our head, right? Up through about partway through the temporal region. So if we get an injury, for example, and we take, you guys remember in clinical correlations you took the sharp versus dull? If we do that up all the way and we find that we can't, one, discriminate sharp versus dull in C2 in the back of the head, and we can't even feel that, then we know the spinal cord injury is in the C2 area. Okay, that's how we use dermatomes. All right, so whatever we were made by, whether God went or whether we evolved that way, it's really convenient for medicine, right? So, clinical significance, it allows us to localize spinal cord lesions. All right, so we've talked about receptors, how we get them to fire action potentials for perception of general senses. We've talked about the pathways that go through the spinal cord to get up to the brain. Now let's talk about the brain. Where are they going? All right, we've already talked about it, the primary somatosensory cortex. What is this right here? The central sulcus, right? In front of that is the motor cortex. Behind that, or posterior to that rather, is the somatosensory area. And it's organized the exact same way. We have our tongue, fingers, hand, shoulder, neck, thorax, thigh, from our upper to lower body as we go up and around here. All right, and our genitals are right smack in the middle. They need to be protected, right? All right, so we call that the post-central gyrus. All right, I said posterior to the central sulcus. That area is technically referred to anatomically as the post-central gyrus. All right, again, highly organized, a lot of spatial organization there. All right, and we know that because all sensory information crosses over either in the spinal cord or the medulla, that whatever we detect on the right, whatever happens in the left hand of our body gets processed right brain. Okay? So everything crosses over. Last fall, one of the students asked me, why? Why does it cross over? Like, how did that come about? And the short answer is nobody knows. The longer answer is they think during some point in evolutionary history, when we went from, I think it was quadrupeds to bipeds, things twisted. They call it the somatic twist. And that kind of reversed things. It's a theory. I can send you guys that information. All right, so in the primary sensory area, this is that sensory homunculus. We talked about homunculus. This is actually what it looks like. So mouth, head, upper limbs, lower limbs, genitals. Okay, in there. Notice that there's unequal representation. So what this motor homunculus also tries to do is say that a lot of sensory information is dedicated to our lips, more so than what's dedicated to, for example, our eyes. All right, so the unequal distribution. But it's funny, I see a lot of you smiling like something. What did I do?
No, I just was making a kissy face when you said that.
Oh.
Sorry, I have to entertain myself.
I get All right. So what that means, what that means is we have a lot of sensory receptors dedicated to our lips. So our lips should be very what? Sensitive. All right. Lower trunk, least sensitive, and that makes sense. You guys ever in like an anatomy and physiology lab have done that 2-point discrimination where you take like a almost looks like a, what do they call it, a compass, 2 points, and then do you feel that as 2 points? No. Do you feel that as 2 points? Yes. And the width is much smaller in your finger than it is, let's say, in the back of your neck. This is why. This is one of the reasons why. All right. Remember, this is our primary somatosensory cortex. The parietal area is involved in processing sensory information. So these areas in green and red here are what we refer to as our somatosensory association areas. So they receive information from the primary somatosensory cortex and connects that with visual information and auditory information, taste, smell information, and puts that all together. Okay, connects them. This is where associations are made. So deciphering complex sensory associations